Greetings everyone, let us now try to solve this first example for mathematical induction. Okay, so we need to prove that for all positive integers n, the sum of n consecutive odd integers is equal to n squared. Okay, so if we recall the things that we need to do for mathematical induction, the first one is we need to verify that P1 when n is equal to 1 is true. So P1, what is our P1? N is 1, so we only have one odd integer right here, that B1 is equal to n squared, which would be 1 squared. Now this is true, right? Because 1 squared is equal to 1. Okay, so now we've verified that this is true. Okay, now the second thing that we need to do is we need to show, assuming that pk is true, then we need to show that pk plus 1 is true. So how do we do that exactly? So we will start by writing out pk. So pk, so 1 plus 3 plus 2k minus 1 is equal to k squared. Okay, so we basically substituted k for n. And then pk plus 1. pk plus 1, so what's that? 1 plus 3 plus 5 plus, let's use a bracket here, 2 times k plus 1 minus 1 is equal to k plus 1 squared. Okay, so what we're going to do next is we're going to assume that pk is true. We're going to assume that this is true. And using algebraic operations, if we can show that pk plus 1 is also true, then we have proven this statement for all positive integers. So how does this work? So how do we go about doing this? Okay, so let's copy this pk first. Okay, so we have it right here, our pk. Okay, so if we assume this is true, we need to assume that this is true. So if this is true, the left hand side and the right hand side are equal, right? Now we are going to perform algebraic operations with the goal of obtaining pk plus 1. So if you take a look at the left hand side, how do we obtain pk plus 1 here? So note that this is the k term, right? So how do we gain or obtain pk plus 1? So we need to add another term, right? We need to add another term, which is this one right here, right? In order for this to left hand side to be pk plus 1. So let's do that, just that. 1 plus 3 plus 5 plus dot dot, and then 2k minus 1 plus 2 times k plus 1 minus 1. So we've added something, this number on the left hand side. Therefore, we also need to add to the right hand side, right? Because we should also do that for this statement to be true. So let's add it also on the right hand side. Okay. So this pk right here. So let's recap. From this pk right here, we simply added this to times k plus 1 minus 1 on the left hand side, and 2 times k plus 1 minus 1 on the right hand side. So this is still equal, right? This is still true. This is still true. Okay, now let's take a look. If we simplify this right hand side, what do we get? K squared plus 2k, this is 2 times 1 minus 1, that would be plus 1, right? And if you take a look, this is a perfect square trinomial, and we can express this as k plus 1 squared. Okay, so k plus 1 squared. So this is actually what we got here for pk plus 1. So since we got k plus 1 squared, therefore we proved that this is also pk plus 1 is also true. So we started with a true statement, so we assumed that pk is true. We started with that one, and then we simply added two equal numbers or expressions here to the left hand side and right hand side, making it still true. And then we arrived at this, we arrived at pk plus 1, right? This is k plus 1 squared. Therefore, uh, we can conclude that pk plus 1 is also true. Now that we've established that, we now know that this statement right here is true for all positive integers. Now, why can we say that? Because again, we know that p1 is true. Now that we've proven that if pk is true, then pk plus 1 is true, we can also say that p2 is true because p1 is true. And then p3 is true because p2 is true, and so on until infinity. So we've actually proven it. Okay, so this is how we do the mathematical induction, and in the next few videos we will do some more examples so that we can improve our understanding of this. Okay, so thank you for watching this video. I hope you learned something, and I will see you in the next video.